Hey everyone, I'm Mukayis, and today we are going to solve this problem. Actually, this problem is one of my final tests in Introduction of Functional Analysis. So the problem is let x is equal to C0 R with a space of continuous functions vanishing at infinity, where C0 R is equal to limit absolute x approach to infinity of fx is equal to 0, where f elements are. We define a norm by norm f is equal to supremum of absolute value of fx. We want to prove that the pair of norm with a space is a Banach space. Let me define what is a Banach space. A Banach space is a norm space which is a complete metric space. And firstly, we want to show that the pair of norm with a space is a norm space. What is a norm space? A norm space is a vector space with a metric defined by norm. So we can form a function from a space to a scalar like this. Here is the representation. The function is represented by the bars because norm is represented by the two bars. X is the space and R is the scalar. This space is said to be a norm space if it satisfies some of the axioms, because a space must have underlying field. So the field may be real numbers or this complex number. It depends on the nature of the function. Axioms of norm space. The first axiom is if we take any element from the space X and the element is represented by F. Here, if F is an element that was taken from the space, then the norm of that F must be positive. It can be negative, as the definition of the length says total of the length of a vector must be positive or 0. So the first axiom is for all of the elements that was taken from the space, the norm of all the element must be greater than or equal to 0. The second axiom is if the norm of any element that was taken from the space and is 0, then we can say that the vector or the element is 0. And this is also true the converse, that if any element is 0, then its norm or length is also 0. The third axiom is if we are going to see the norm of scalar multiplication alpha and f, where alpha is a member of the field, then it must be equal to the magnitude of the scalar with the norm of f. And the last axiom is the triangular inequality. We are going to see the norm of the two elements, the addition of the two elements from the space, and that must be less than individual norms of the two elements if the space and the taken the sum of it. We start from first axiom. We define norm by norm f is equal to supremum f of absolute value of fx. We know that one of the properties of absolute value is absolute value must be greater than or equal to 0 for each x element R. Since absolute value of fx greater than or equal to 0, then the supremum of absolute value of fx also greater than or equal to 0. So that we can say that the first axiom satisfies that the norm of all the elements must be greater than or equal to 0. Next to second axiom is right hand set and left hand set. We start from right hand set. Right hand set is if norm f is equal to 0, then f is equal to 0. We get like this, so that fx greater than or equal to 0 and fx less than or equal to 0. It must be fx is equal to 0 for each x element R. Then we get that f is equal to 0 is 0 function. And the next is left hand side. Left hand side, if f is equal to 0, then norm f is equal to 0. Since fx is equal to 0 for each x element r, then 0 is the upper limit of f. Hence we get that supremum of absolute fx less than or equal to 0 and supremum of absolute value of fx greater than or equal to 0. Then it must be supremum of absolute value fx is equal to 0. Or in the other word, we can say that norm f is equal to 0. So that the second axiom satisfies. Next is the third axiom. Using by the properties of absolute value, that absolute value of alpha times fx is equal to individual two elements of alpha and fx, and alpha independent to x. Then uh, we we will get that norm alpha times f is equal to individual of two element is alpha and f. So that we can say that the third axiom satisfied. And the last axiom is the triangular inequality. We define the norm f, g, and f plus g like that, and according to triangular inequality, that a plus b less than or equal to absolute of a plus absolute b. And then we get supremum of absolute fx plus gx less than supremum of absolute of fx plus absolute of gx. And then we let a is equal to supremum of absolute fx, where r subset of r, and since supremum a plus g is equal to a plus supremum of g, where a subset or of r and g element r, we get that supremum of absolute fx plus supremum of absolute gx. And then we know that before we define that norm f is equal to supremum of absolute fx, and norm g is equal to supremum of absolute of gx. And we can say that the last axiom satisfy. So if that function satisfy the four properties for the properties of a norm space, then we can say that the pair of the norm with the space is equal to a is equal to a norm space, or we can say that a non-linear space. Okay, the next is completeness. Let fn is Cauchy sequence in x, and then we define like this, and we we will show that fn converges to f for an approach to infinity, or fn converges to f element cr. And there is a function f element cr such that norm f minus fn converges to 0, where we define norm f is equal to supremum of absolute fx. Okay, we will show that fn in C0 R is a Cauchy sequence in R for a fixed alpha. And to show number 2, then take the fixed alpha in C0 R, where alpha element C0 R such that we get like that. Since norm fm minus fn less than or equal to epsilon for each nm greater or equal to n from part 1, and we get that like this, so that fn alpha is Cauchy sequence in R. Since R is Banach space, then fn alpha is convergent sequence. Okay, we want to show that fn convergence converge to f for an approach to infinity such that norm f minus fn converge to 0. From the equation this from part 3, okay, we let m approach to infinity, then fm alpha converge to alpha f alpha for each m greater than or equal to n. And for each epsilon positive, there are n element n. For each n m greater than or equal to n, such that norm of f alpha minus fn alpha less than or equal to epsilon, and we get norm f minus fn is equal to supremum of absolute f alpha minus fn alpha less than or equal to epsilon. It is shown that norm f minus fn converges to 0 for an approach to infinity. Okay, next we want to show that f element C null R, and the first take epsilon positive. There is an element n such that like this with norm f supremum absolute fx. Then we get supremum absolute of fx minus fnx less than epsilon, or absolute value of fx minus fnx less than or equal to epsilon. According to properties of absolute value, that absolute value of alpha less than epsilon is equal to minus epsilon less than alpha less than epsilon, such that we get that like this. Okay, from this to this. Okay, we know that the value of limit epsilon is epsilon because it's constant, and also limit of fnx is equal to 0 since fn converges f, where f element R, then limit of fx is equal to 0 such that fn converges to 0 at absolute value of x is convert approach to infinity. Then we get that minus epsilon less than limit fx less than epsilon for each epsilon positive. To determine limit fx, we are using sandwich theorem because it's between minus epsilon and epsilon. For each epsilon, then we get that limit of fx is equal to 0. Okay, before we have proof that that is a norm space and completeness, and we can say that the pair of the norm with the space is Banach space.